Runtime polymorphism is the ability of a program to decide which implementation of a function to execute, while the program is running based on the actual derived type of an object. In C++, this is achieved by declaring a member function as virtual in a base class. Class animal open brace public colon virtual void make sound const equals 0 semicolon close brace. Concrete derived classes such as dog, cat, and bird each provide their own definition of make sound. When we store a pointer or reference to a base class animal star, a equals new dog semicolon, a arrow make sound open parenthesis close parenthesis semicolon, the call make sound is resolved at runtime via the object's hidden v pointer, causing the dog make sound implementation to execute. This eliminates the need for manual if-else or switch statements that would test the concrete type, leading to cleaner extensible code. A graphics engine can keep a container std : vector less than shape star greater, where each element may be a circle, rectangle, or polygon. A single loop for open parenthesis auto star s : shapes close parenthesis s arrow draw open parenthesis close parenthesis semicolon draws every shape correctly because draw is virtual. Declaration -virtual keyword in the base class. Dynamic dispatch - the compiler generates a vtable semicolon. The call is looked up at runtime. Extensibility - adding a new derived class never forces changes to existing client code. Safety - the base class can be abstract equals 0 to force implementation in derived classes. This mechanism is the cornerstone of object-oriented design in C++ and underpins many design patterns such as strategy and visitor. When a class contains at least one virtual function, the compiler creates a hidden virtual table, also called vtable, for that class. The vtable is essentially an array of function pointers, one entry for each virtual function declared or inherited by the class. Every object of such a class stores a hidden pointer, the v-pointer, typically as its first data member. The v-pointer points to the vtable belonging to the object's dynamic type. Step 1. The expression obj arrow virtual function parentheses is compiled into code that first reads the object's v-pointer. Step 2. Using the offset of virtual function within the vtable, the program fetches the appropriate function pointer. Step 3. The CPU jumps to the fetched address and executes the concrete implementation. Because each derived class builds its own vtable, which may reuse entries from the base class but can replace overridden functions, the same object, no matter how many inheritance levels deep, always knows which table to consult. This design gives a one lookup time, a single dereference of the v-pointer, and a single indexed read from the table. Multiple inheritance adds a second v-pointer for each distinct base sub-object, and the compiler may generate virtual inheritance tables to resolve the diamond problem, but the fundamental principle remains identical. Struct base with a virtual function f that prints the word base. Struct derived inherits from base and overrides f to print the word derived. Base pointer p is assigned a new derived object. The pointer's v-pointer points to derived's v-table. Calling p arrow f invokes dynamic dispatch and prints derived. Understanding the v-table layout helps when debugging issues such as calling a pure virtual function from a constructor, because the v-pointer still points to the base class's table, where the entry may be a placeholder that aborts. The v-table is a low-level mechanism, but its existence is transparent to most C++ programmers. They simply rely on the virtual keyword to get the desired runtime behavior. Overriding a virtual function means providing a new definition in a derived class that replaces the base class version when invoked through a base pointer or reference. The C++ language enforces strict signature matching to guarantee that the two functions are interchangeable. Name must be identical. Parameter list, number, order types, CV qualifiers and ref qualifiers must match exactly. Return type must be the same or be covariant. A covariant return type allows the derived override to return a pointer or reference to a class that is derived from the base's return type. This preserves substitutability while giving callers more specific information when they know the concrete type. Example of exact match. A struct base with a virtual function compute taking an int x and marked const. A struct derived inheriting from base defines int compute taking an int x const and override. This is okay. If the derived version adds a default argument, changes int to long, or makes the function non-const, the compiler will reject the override. Example of covariant return. A struct animal with a pure virtual function clone returning a pointer to animal and marked const. A struct dog inheriting from animal defines dog pointer clone const and override. This is okay because dog pointer is derived from animal pointer. The rule only works for pointers and references. Returning a plain object of a derived type is not covariant. Why strict matching matters. It ensures the Liskov substitution principle. Any object of the derived class can stand in for an object of the base class without breaking client code. If signatures differ, a call through a base pointer could invoke a function with an incompatible prototype, leading to undefined behavior. Modern compilers can warn about hidden overloads when a derived class inadvertently declares a function with the same name but a different signature, marking the base function virtual, and the derived one with override eliminates this class of bugs. Practical tip: always use override and optionally final on overridden virtual functions. The compiler will verify that the signatures match and report an error if they do not, catching mistakes early. An abstract class in C++ is a class that cannot be instantiated because it contains at least one pure virtual function. A pure virtual function is declared by appending =0 to its prototype. For example, class shape public virtual void draw const equals 0, and pure virtual no implementation here virtual double area const equals 0 virtual destructor equals default destructor can be virtual but not pure. Equals 0 tells the compiler that the function has no definition in the base class. Any concrete derived class must provide one, otherwise the derived class itself becomes abstract. No objects of the abstract class, shape S is ill-formed. Interface definition: the abstract class acts as a contract, defining the set of operations that all concrete subclasses must support. Partial implementation: an abstract class may still provide implementations for non-pure virtual functions, allowing code reuse. For instance, shape could implement a generic print that uses area and draw. Construction order: when constructing an object of a concrete subclass, base class constructors run first. However, during base class construction, the dynamic type of the object is still the base class, so calls to virtual functions including pure ones resolve to the base version. Since pure virtual functions have no body, invoking them from the base constructor leads to a runtime error pure virtual function call. Therefore, never call virtual functions from constructors or destructors. Class circle public shape double radius public circle double r colon radius r braces void draw const override open brace std count less than quote drawing circle quote close brace double area const override open brace return 3.14159 times radius close brace. Now circle C 5.0 is legal, and C.draw and C.area work as expected. Abstract base classes are the backbone of interface-driven design, enabling polymorphic containers std vector of unique pointer of shape and facilitating patterns such as factory and strategy. Object slicing occurs when a derived class object is copied into a base class variable by value. The copy constructor of the base class only copies the base subobject, discarding the derived part. Struct base open brace int id semicolon close brace. Struct derived colon base open brace double extra semicolon close brace. Derived d open brace 1, 3.14 close brace. Base b equals d semicolon slicing dash extra is lost. From the programmer's perspective, the original object's full state is sliced away, leading to incorrect behavior and subtle bugs, especially when virtual functions are involved. The v pointer in the sliced object points to the base's v table. Solution: work with pointers or references to the base class rather than by value. Since the pointer or reference refers to the original object, the complete derived object remains intact, and virtual calls dispatch correctly. Base star p equals new derived open brace 1, 3.14 close brace semicolon or std colon colon. Unique pointer less than base greater than up equals std colon colon. Make unique less than derived greater than open parenthesis close parenthesis semicolon. This approach also enables interface-driven design. The base class defines a contract, pure virtual functions, and any number of concrete types can implement it. Client code depends only on the abstract interface, not on concrete implementations. Benefits of interface-driven design. Decoupling, components can be compiled separately. Changes to a concrete class do not require recompilation of users. Testability, mock objects that implement the same interface can replace real implementations in unit tests. Extensibility, new derived types can be added without touching existing code, open-closed principle. Practical pattern, the strategy pattern stores a reference to an abstract algorithm interface. The concrete strategy quicksort merge sort is selected at runtime, and the client calls algorithm arrow run open parenthesis data close parenthesis semicolon. Because the client holds a pointer or reference, there is no slicing and the correct overridden run method executes. Key rule, never store derived objects by value in a container of base objects. Use std::: vector less than std::: unique pointer less than base greater than or std::: vector less than std::: reference wrapper less than base greater than to preserve polymorphic behavior. Virtual function call incurs extra work compared to a non-virtual direct call. Load v-pointer, read the hidden pointer from the object, usually one memory load. Lookup in v-table, index into the table and fetch the function pointer, another load. Indirect jump, transfer control to the retrieved address. The cost can be modeled as cost virtual equals cptr plus clookup plus cbody, where cptr and clookup are each a few CPU cycles, typically 1 to 3 cycles on modern CPUs, and cbody dominates for any non-trivial function. Inlining, because the target address is not known at compile time, the compiler cannot inline a virtual call in the general case. Inlining eliminates call overhead and can enable further optimizations, constant propagation, dead code elimination. However, modern compilers perform virtualization. If they can deduce the concrete type statically, for example the object is a local variable of a known derived type, they replace the virtual call with a direct call and may inline it. Cache effects, the v-table resides in memory. If it is not already in the CPU L1 or L2 cache, fetching the function pointer can cause a cache miss, adding latency tens of cycles. In tight loops that call a virtual function millions of times, this overhead becomes measurable. Strategies to mitigate are as follows. Final classes, marking a class final tells the compiler that no further overrides exist, allowing devirtualization. Reserve objects contiguously. Allocating objects of the same dynamic type together improves locality of the v-pointer and v-table. Profile guided optimization, PGO, helps the compiler identify hot virtual calls and optimize them. Rule of thumb, if the virtual function does substantial work, for example input, output, or complex calculations, the dispatch overhead is negligible. If the function is a tiny accessor or mutator, consider making it non-virtual or using inline with final to avoid unnecessary indirection. Benchmark example pseudo-code. Struct base open brace virtual int get const open brace return value close brace semicolon int value semicolon close brace. Struct derived final colon base open brace int get const override open brace return value close brace semicolon close brace. Void loop taking base pointer b open brace for int I equals 0. I less than 1 million. Increment I close brace sum plus equals b arrow get parentheses semicolon virtual call close brace. Compiling with O3 and March equals native often results in the compiler devirtualizing the call because b points to a derived final object, turning the loop into a direct load of value and eliminating the indirection. Cost virtual equals cpointer plus clookup plus cbody. Cpointer time to read the object's vpointer, a single memory load. On a modern superscalar processor, this is typically 1 to 2 cycles if the pointer is in cache. Clookup time to index into the v-table and fetch the function address, another load. This also costs 1 to 2 cycles, plus any potential branch predictor penalty for the indirect jump. Cbody time spent executing the actual function body, which depends on the algorithmic complexity of the function, O of f. From a complexity theoretical perspective, both cpointer and clookup are O of 1 operations because they do not grow with input size. Therefore, the overall asymptotic complexity of a virtual call is dominated by the complexity of the function body. Cost total equals O of 1 plus O of 1 plus O of f equals O of f. The constant factor cpointer plus clookup is the dispatch overhead. It is irrelevant for big O analysis, but crucial in performance-critical contexts. For example, inner loops, high-frequency trading, real-time graphics. If a program makes n virtual calls, the expected total dispatch time is n times the sum of C pointer and C lookup. Assuming a cache hit rate h for v pointers and v tables, the effective cost becomes n times the quantity h times the sum of C pointer and C lookup, plus open parenthesis, 1 minus h close parenthesis times the sum of C pointer and C lookup plus miss penalty, where miss penalty may be 30 to 100 cycles on a typical CPU. Reducing n, the call frequency, or improving cache hit rates by grouping objects of the same dynamic type directly lowers the total dispatch overhead. This quantitative view aids decision-making when profiling reveals that virtual calls dominate execution time. While virtual dispatch does not affect algorithmic complexity, its constant time overhead can be modeled, measured, and minimized using caching strategies, final classes, and devirtualization techniques. Virtual functions are the engine behind many classic design patterns that require runtime selection of behavior. Strategy pattern. The strategy pattern defines a family of interchangeable algorithms encapsulated behind a common abstract interface. Class sort algorithm declares a pure virtual function sort that takes a reference to a vector of integers and is const, and a virtual default destructor. Class quicksort inherits from sort algorithm and overrides sort with a quicksort implementation. Class merge sort inherits from sort algorithm and overrides sort with a merge sort implementation. Class context holds a unique pointer to sort algorithm named algo, provides a method set strategy that moves a unique pointer into algo, and an execute method that calls the virtual sort on the data through algo. The call algo arrow sort of data is virtual. The concrete algorithm can be swapped at runtime without modifying context. Template method pattern. The template method defines the skeleton of an algorithm in a base class, delegating some steps to derived classes via virtual hooks. Class document processor provides a public method process that calls load, then the virtual hook parse, then the virtual hook validate, and finally render. It declares pure virtual functions parse and validate for subclasses to implement, and protected concrete methods load and render with common code. Class XML processor inherits from document processor and overrides parse with XML parsing and validate with XML schema validation. Only parse and validate vary, while process controls the overall flow. Factory pattern. A factory hides object creation behind a function that returns a pointer or reference to an abstract base. Class shape declares a pure virtual draw method and a virtual default destructor. Class circle and class square both inherit from shape. The function createShape takes a string type and returns a unique pointer to shape. If the type is circle, it creates a circle. If square, it creates a square. Otherwise, it throws an invalid argument exception for unknown shape. Client code calls createShape with the string circle, receives a pointer to shape named S, and then calls draw on S without knowing the concrete class. Why virtual functions matter. They provide polymorphic dispatch needed for these patterns to work. Without virtual dispatch, the factory would have to return void pointer, and the client would need explicit casts. The strategy would need a large switch statement instead of clean object-oriented substitution. Practical tip: mark strategy and template method base classes as protected or final where appropriate, and use override to catch signature mismatches early. Employ unique pointer or shared pointer to manage object lifetimes safely. These patterns illustrate how a small language feature, virtual functions, enables highly modular, extensible architectures that are easy to test and evolve.